Hello. The topic for our data science project was to analyze the weather history data set as well as a rain history data set. So let me just share my screen. Okay. So coming to the explanation of our project, the first two cells is to import the required libraries, including pandas, matplotlib, seaborn for plotting purposes, sklearn, and so forth. We've mounted our data set onto the Colab environment. Okay, so the data types of the attributes, there are the nominal data includes summary, precipitation type, and daily summary. And the interval data are temperature and apparent temperature. So as you can see, we've printed the first 5 rows and the last 5 rows of our data set using the dot head and dot tail functions respectively. The shape of our data set is 96,453 rows and 12 columns. The columns being temperature, apparent temperature, humidity, wind speed, so on and so forth till pressure. The description of our data set, we've printed out the count, that is the number of values under each column, present under every column, the mean of the values, the median of the values, the standard deviation of the values, the minimum and the maximum values under each column. Df.info is to describe first of all, the number of values under each column, their data type, and also to show if it is null or not null. Upon checking the data types, upon checking, Next, moving on, we've printed the categorical variables and the quantitative variables. Our categorical variables printed being formatted, date, summary, precipitation type. Quantitative variables, as you can see, temperature, apparent temperature, humidity, till pressure. Okay, next, moving on, we are checking to see the number of null values in every column. So as we can see here, all the columns have 0 null values except for precipitation type. So we have chosen not to overlook this one blemish by using the .fillNow method, that is fillNow function. After that, we've printed the number of values in the rain and snow precipitation type. That is, there are two precipitation types being rain and snow, and we've printed the number of rows that fall under either rain or snow. Okay. Next, moving on, we come to the normality test. So what the normality test in the normality test, what it aims to do, it's used to determine whether the sample data that has been drawn, whether it has been drawn from a normally distributed population. A normally distributed population is one where if it's within some sort of like limit, like within some tolerance. Okay. So the normality test, we've used the histogram plotting for this in order to test normality. As you can see, okay, coming to as you can see, humidity over here is left skewed. The number of is a left skewed distribution. Wind speed is a right skewed distribution. Temperature and apparent temperature, they are normally distributed. That is, we find equal number of data points on either side. As okay, temperature, apparent temperature, and wind bearing degrees are all normally distributed. Okay, moving on. Right. So under the summary column, we are just counting how many rows, how many values belong to each category of summary. These are the different categories under summary: partly cloudy, mostly cloudy, and so on, breezy and dry. There are about I think there are about 15 different types of summary values. So we've just printed the number of rows belonging to each category of the summary. Visualizing this, in order to just visualize it, just to make it more appealing and more understandable, we visualized it as follows. Okay. Next is the count plot. As to we've already counted the number of rows that belong to the rain and the snow precipitation types. This is just to make it visually appealing and to make it more understandable. Okay, so coming now to the time series plot, I have plotted a time series of precipitation type against humidity. Sorry, not humidity. The first plot is to show temperature versus precipitation type. The time series, the second time series plot is humidity versus wind speed. And the third one is temperature versus daily summary. The x-axis is very clustered, very clamped because owing to the number of different types of daily summary. Okay, so next the pair plot, right? The pair plot is to show the pairwise relationship in the data set. So using the pair plot was plotted using the SNS Seaborn library. So this is the pair plot. All of these are the data points that have been distributed. Okay, next coming to the box plot. So I have plotted So I have plotted a box plot for I'm plotted wind bearing degrees on the y-axis and precipitation type on the x-axis. So the two being rain and snow again. So the first line we can see is the minimum value. The second line, this one, is the Q1, that is the first quartile value. The green line that we see here is the median value. The next line here is Q3, that is the next quartile Q3, the second quartile, and the last one is the maximum value. So for wind bearing, we can see that the median is about 175. The minimum value for both rain and snow data types are 0. Maximum value for rain is 355 and for snow as well 355. Right. And in what is important to note is that 25% of the data values, or the number of data values, fall between the minimum value and Q1. Same applies between median and Q3. And the median is such that it separates 50% of data values on either side of it. Box plots have also been plotted for apparent temperature versus precipitation type. Okay, right. Now coming to hypothesis testing, we've used the Z-test in order to go ahead with the hypothesis testing. So we've used here. So what the test that we've used here is a two-sided test. It is a two-sided test where the value of Z is at 0.05 significance level, making it 0.025 for the two-sided test. And from the Z table, we know that it is plus or minus 1.96 at a significance level of 0.05. Okay. And because it is a two-sided test, it becomes 0.025. Okay. Right. So coming here, we've used the Z-test, the formula over here. As you can see, mean data minus high mean divided by standard population divided by the square root of n. Okay. So from this plot that we've added comments just for reference sake. Okay, so as we can see here, the Z-score that is calculated is 2.34, and it is greater than our calculated tabular Z-score being 1 plus 1.96 on the right-hand side of the plot, obviously. And so we reject the null hypothesis. Next, we see we would have also on the left-hand side, we would have got minus 2.34, and this is lesser than minus 1.96, and so we reject the null hypothesis. The critical value is plus 1.96. Next, the p-value. So the p-value at if the p-value is less than 0.05, then we can reject the null hypothesis. If the p-value is greater than 0.05, then we fail to reject the null hypothesis. That is, we accept the null hypothesis. Okay. So the observed z value, right? The observed p-value here is 2.56. There are a lot of decimal points, e minus 0.5, and this is definitely lesser than 0.05. Hence, we reject the null hypothesis. Okay. Next, coming to linear regression. So in order to show linear regression, we've calculated our true negatives, false positives, as well as true positives. We've printed accuracy, precision, and recall. Okay, so this is the plot that we have got for our linear regression. Right. And so, sorry, I forgot to mention the two parameters that have been used for the linear to plot the linear regression for the linear regression model. It's temperature and humidity. Okay. So the accuracy we have achieved is 0.8655 being 86.5%, precision being 86%, and recall being 99%. Okay, so just to note, precision it refers to the percentage of our results which are relevant. Recall refers to the percentage of the total relevant results that have been correctly classified by the model. Higher the precision, it means that the algorithm is returning more relevant results than the irrelevant ones. Okay. So next, we've just described all of the data types, that is, which includes our numerical as well as categorical data types. Next, coming to the correlation. So correlation, it ranges between +1 and -1. +1 indicating a strong correlation, -1 indicating a negative correlation. Sorry, and 0 indicating no correlation. Okay. So as we can see here, temperature and temperature and apparent temperature are highly correlated. As we can see, 0.99, almost close to 1. Apparent temperature and visibility are not that, they are positively correlated, but it is not strongly positively correlated. Same applies, humidity and visibility, as you can see, are negatively correlated. Visibility and humidity are negatively correlated. Visibility and apparent temperature are slightly positively correlated. Okay. Right. So next we are visualizing the data, the relationship between temperature and the other dependent variables. Other dependent variables, one, the first parameter being humidity. So this is a plot for temperature versus humidity. That is a scatter plot using the REG plot function. Right. So from this graph, we can see that there is a negative sort of correlation between humidity and temperature. And also we can see there are quite a few outliers. So now we are going to remove the outliers. In order to remove the outliers, we are defining, it is based on the Z-score, and we're using standard deviation, and we're setting the condition as saying standard deviation greater than 3. So, right. Sorry. Yeah. So the z-scores are the number of standard deviations above and below the mean that each value falls. If the z-score of a data point is more than 3, then it indicates that this data point is quite different from the other data points, and hence we're going to ignore it. That is because it's on account of being an outlier. Okay. So, right. After removing the outliers, this is a new plot that has been formed to better show the negative correlation. Next, a scatter plot has been plotted for temperature and apparent temperature. We can observe that there is a strong positive correlation between these two parameters. And this has already been proved by the tabular column, that is, by the tabular data that has been displayed, that had been displayed above. Next is the scatter plot between temperature and visibility. We can't really see any strong relationship that is either negative or positive. Hence, we can drop this, we can ignore this relationship basically. Okay, right. So next, we are splitting the data set into the training and testing, in a training and testing ratio of 80:20, 80% being training and, training and 20% being testing. Next, to fit our training data for the linear regression model. Okay. Right. So we've got the predicted, that is the we predicted the test set result. Next we are printing the regressor score, that is the R score, the R score, and it is 0.9871. Inference from this R square value, it shows us R square, basically it gives us a measure of how well the actual outcomes are replicated by the model or the regression line. R square is always between 0 and 1, that is from 0 to 100%. A value of 1 means the model means that the model explains all the variation in the predicted variable around its mean. Right. Here the R square, yeah, it's close to 1. That is it 0.9871. It means it is a good fit. R square values approaching 1 are indicating of high accuracy between the observed and the predicted values. Okay. So next, coming to reading the rain history data set. This is our second data set. So this we have just printed, sorry, just went scroll down top. Let's see. Okay, so here we are. This is the rain history data set. We've counted the number of values under each column. Right. So these, as you can see, are the number of columns here: date, location, minimum temperature, maximum temperature, rainfall, wind, gust speed, wind direction at 9 a.m., at 3 p.m., and so on and so forth. We are just printing out all the values under each column. Okay. So yeah, this is the shape. That is, there are 1,12,925 rows and 17 columns. Right. So now in the rain today and rain tomorrow column, we're replacing, instead of no, we're putting 0 and 1. Instead of basically yes and no, we're putting the values 0 and 1, 0 for no and 1 for yes respectively. Okay, so we're printing out the categorical values here, being wind gust speed, wind direction at 3 p.m., wind direction at 9 a.m. We're using the min-max scaler in order to normalize the data set. Next, we're calculating the correlation matrix. The correlation matrix for under the columns rain tomorrow. Okay. Next, yeah. Okay. Next, we're going to use ML algorithms to predict whether it will rain tomorrow using a binary classification model. Again, we're importing the train test split in order to split the data set into train and test data. Okay, the test size being 0.2, that is 20% is test size, and 80% of the remaining data set is for training purposes. First thing we're doing is logistic. We're using, first algorithm is the logistic regression algorithm. Okay. So upon plotting the confusion matrix for the logistic regression, we get the following confusion matrix. As you can see, there are, right, there are 16,693 values that have been correctly classified as being false. That is, there are 16,693 true negatives. There are 2,472 false negatives. There are 2,491 true positives and 929 true false negatives. Okay. Next, we are printing the test score being 0.849, that is 84.9%, almost close to about 85%. Next is the decision tree classifier. We've trained the model, predicted the values. Okay. Next is again we've plotted a confusion matrix. As you can see, the number of false, number of true positives is 2,685. The number of false positives 2,357. Again, we printed and so on and so forth. Again, we printed the test score being 0.7947. That is 79.47%. Next is the random forest classifier. Again, we've printed out the confusion matrix. printed out the test score as well, being 0.855, that is 85.5%. You can round it, which we round off to 86%. Next is the naive-Bayes classifier. Usually the naive-Bayes classifier requires, no parameters. It requires training of parameters, and therefore it's a little more complex. We've plotted the confusion matrix and printed the score as well. The score being quite low compared to the others, 0.721, that is 72.1%. The final one is the KNN, that is the K nearest neighbor classification. Right. And the test score obtained for this is 81.68%. Okay. So the main reason was to see how well these algorithms ran for our in order to predict whether it was going to rain tomorrow. So based on these scores, we can see that the score that the random forest score is the best among all of them. Among all of them, it's the best. Right. These are the confusion matrices. We've just printed it out again just for clarity purposes, all in one space for different algorithms. Okay, next, coming to the ROC curve. So the ROC curve for the model, it takes basically what the ROC curve, it returns the false positive rates for each threshold, true positive rates for each threshold, and also the thresholds. That's what the ROC curve returns. FPR being false positive rates, TPR is the true positive rates. So we've printed the ROC curves for all the algorithms. That is all the 5 algorithms that I just showed. Okay. So this is the graph. This is the figure. ROC curve for logistic regression, for naive-Bayes, for decision tree, for random forest, and this one for KNN. Sorry. The results indicate that the random forest technique presents the best results in terms of prediction, and also to point out, the random forest showed the best test score as well, being 86%. And the random forest technique is followed by the SVM and logistic regression with test scores close to 85%. The worst results were present for the naive-Bayes, which may be associated with the assumption, particularly the assumption of independence. Basically, the parametric methods, naive-Bayes and logistic regression, they have a higher speed in learning the data in contrast to non-parametric methods, which require more time to train the parameters. Right. So considering the computation time within the best scores, logistic regression exhibits the best result, followed by random forest, while SVM requires considerable time to perform the calculations. Next, we're just doing visualizations for using violin plot. Okay, so what the violin plot does is, there is a tiny white dot here, and that white dot is basically the median, it displays the median value. So that we have plotted a violin plot for precipitation type, temperature versus precipitation type. Okay. And the black line over here signifies the interquartile range, the first quartile, the third quartile, that is, and the third quartile. The lowermost point here is the lower adjacent value, and the uppermost point here, over here is the upper adjacent value, and the other points, the remaining points, are the outside points. So we've plotted violin points for, violin plots for precipitation type versus temperature. Next, precipitation type versus humidity. This is the reason why we're using a violin plot, is because it gives slightly more clarity as opposed to a box plot. Okay. So next, what we're doing is we wanted to basically make violin plots for different months. So what we've done is we've taken these dates in the date column, and we split the dates in order to make it year, month, and day, being like 31st, 1st, and so on. So according to the months, we have plotted violin plots here. Yeah, as you can see. So the month here is the 1st, 2nd, 3rd, 4th, so on till the 12th month. And we plotted apparent temperature versus month. So it just gives more clarity. This is the plot for it. Next, we've plotted the box-in plot. Yeah. So we plot the box-in plot. Same thing, we've used all the months on the x-axis and apparent temperature on the y-axis. Next, the rel plot is the rel plot is to show the rel plot is a basic plot and it's used to show the relationship. It's always been used to show the relationship between two variables, and we've used summary here as a hue, and these are the different data points. Okay, right. Last thing we've used, sorry, the next one is the joint plot. The joint plot displays the relationship between two variables, bivariate, as well as for univariate variables. It's a convenience class that, sorry, this plot is a convenience class that wraps the joint grid. So we plot a joint plot for humidity versus apparent temperature. Right. Next is the LM plot. The LM plot is just used to show the relationship between humidity and apparent temperature. MS over here denotes the month starting. So what we've done is we've used the starting of every month, right? We've used the starting of every month. We've taken the mean of apparent temperature and humidity from these columns respectively, and we've used ms because in order to calculate the mean for the two columns, apparent temperature and humidity, and apparent temperature and humidity. Yeah, so next we're displaying the average apparent temperature and humidity using this mean function, and this is a final plot that has been obtained. Okay, so this was our data science project. The team consisted of um, Nidhi, Manjunath, me, Hrithi Narayan, Manasa, Saumya, Nikhil, Kabir, Nikhil, yeah, Nikhil I've already mentioned, um, and yeah, if I'm forgetting anyone's name, I'm sorry, but the list, we will be uploading a list of our team members along with a separate document onto our Google Drive. Okay. Okay. Thank you.